Okay. So, last class we were discussing the history of the first law of thermodynamics. We didn't quite cover everything that I wanted to get through, so I wanted to recap just a few quick things before we move on to the second law. So really, the first law should really just be thought of as energy conservation. So the general conservation equation, like we mentioned before, accumulation. This is generally going to be your differential term, like how much does the energy of the system change, the mass of the system change, entropy of the system change, I would say. So you can think of this one as mathematically dx dt, the rate of change of some process variable that's being conserved. In minus out plus generation minus consumption is our general balance equation for chemical engineering. Now in the case of mass and energy, we cannot have any generation and consumption. In the case of entropy, we actually can have generation. We'll be talking about that today. Can't really have any consumption in the general balance equation for that. So, when we were doing the application of the first law, so what we talked about was this form of the first law. But that's not necessarily what we use as a chemical engineer to solve a real process problem. So what we're going to do instead is we're going to keep track of all the different ways that energy can enter the system, all the different ways that energy can leave the system, and all we're doing is being accountants for energy. That's what the first law is. So the general form that we'll see in chemical engineering textbooks, or a lot of engineering textbooks, is we're going to have a rate of change of the total energy of the system. So it's not necessarily going to be just internal energy. We can have the internal energy, and in modern sense, we know that this corresponds to the energy that's stored in molecular motion, bond vibrations, molecular rotations, all that different stuff. Kinetic energy is going to be the bulk of it, though. Plus some terms that correspond to sort of standard dynamics and potential energy. In this case here, we have kinetic energy of the entire system, and this is potential energy. This could be electrical potential energy. It could be gravitational potential energy. For the most part, we're going to think of this as gravitational because we're not going to be doing too many electrochemical processes or anything like that. But this sort of term right here is for potential energy, and it can take a number of different forms. So this is going to be equal, so this is our accumulation term, to everything coming in and everything going out of the system. So for every stream flowing into the system, I'll call that K. Every stream going to all the total streams coming in. We're going to have a mass flow rate of that stream, positive for entering, negative for leaving, right? Are you adding to the system or taking away from the system? We use enthalpy instead of internal energy. I'll go over the nomenclature really quickly just in a moment, actually. All right, so what we're doing is we're keeping track of all the energy flowing into the system in the form of enthalpy, which is mostly internal energy, velocity, and potential energy. In addition, we also have heat potentially flowing into the system and work flowing in or out of the system. Now this is a source of much contention, whether or not we put this as a positive W or a negative W. I stand on the side of I don't care. Right, so every time I ask you a question about work, I'm always going to say, is it work into or out of the system? I'm not going to rely on seeing that you have a negative sign and I know what that means. Particularly because when you have a system, like a heat exchanger, where you have two separate processes, you can never keep a constant convention, right? Q has to be positive in one and negative in the other. So Q is most generally positive going into the system, whereas work is conventionally positive going out of the system. So in this case here, the drawing, what we're talking about is a box with multiple flow rates in, multiple flow rates out. And in this case here, as I've drawn it, I've drawn Q going into the system, and I've drawn work going into the system. So based on how you draw your process flow diagram determines whether or not you consider this a positive or a negative. Because let's say that the heat was coming from some sort of a different box. Let's say a furnace where I was burning methane to make CO2 plus other stuff. In this case here, Q would be negative, so I would have a minus Q, right? I'm just keeping track of all the ins and all the outs. That's all that an energy balance is. Just being energy accountants. So quick notation here. So H, we're defining as U plus PV. In just in a moment, I'll talk about why we're defining it this way. The next thing is that the H hat, according to the nomenclature of the Sandler book, this is a asset and a detriment of the book that we're using. It's very meticulous in its notation. H hat would correspond to joules per kilogram, whereas H underbar would correspond to joules per mole. Very precise nomenclature in this book. So I'm trying to adhere to the same one. One other quick note is that the work term, generally for most processes, we are going to look at it as two contributions, something called shaft work. This is going to be if we had some sort of an impeller or a blade or physical object just spinning around and giving the system energy. And we're also going to have PV work. Right? Pressure times volume. So if I were to write out pressure in the SI units of pascals, times it by volume in the SI units, I guess it's meter cubes or just liters? Well, whatever the case, what is a Pascal meter cubed? It's a joule. So PV is energy. So in this case, this would be joules per second. Right? So that's a rate of work. Most often, we look at sort of this term here for an expanding system. If you have a turbine, you can kind of think of it as shaft work that you're pulling out. So this is going to be generally what we will use for most all of the starting calculations on energy balances of processes, particularly power generation, refrigeration cycles, Rankine cycle, Otto cycle, all the different cycles that you would spend a lot of time on in a first semester chemical engineering course or mechanical engineering course is basically just application of this equation right here and using steam tables. Right? The math here is trivial, right? If you say it's steady state, this whole side goes away. All you have to do then is look up what is the enthalpy at a particular temperature and pressure for a steam table, and voila, you've basically solved the whole problem. Yes?
For the equations where we have the summations, the
Mm-hmm.
V is the velocity.
Yes.
But then for all the rest, it's volume.
Oh, yes. So I should be making a little bit more of a fancy cursive V. Sorry. But the good news is that this is the last time you'll basically ever see velocity. So the reason behind that is that U or H is much, much greater in most all of our scenarios than the velocity and any sort of potential energy that we care about. Right, so it's a quick analogy. So imagine you had a bowling ball and you raised it up and you dropped it. How much would the temperature of that bowling ball go up? Probably not a super lot. But when we're talking about chemical engineering processes, we think of it in terms of burning, let's say, methane to make CO2 to heat up a pot of water to cook pasta, for example. So much more energy. Now, that's not to say I won't give you energy balance examples, maybe on an exam or a quiz that takes advantage of this. I've done that in the past where I basically say, here's a meteorite and it's falling to Mars or something. What's the temperature when it hits the ground? Right? If all the energy goes into heating it up. But then again, it's really just a straightforward application of this balance right here. So I consider those kind of questions fair game. Okay, enthalpy. The question is, why do we have this term enthalpy? Why is it defined? Why is it convenient? So I'd like to do this. I had this explained to me, I don't know, probably 24 times when I was an undergraduate, and I still never really understood what it meant. So if we have flow rates coming in, flow rates coming out. How does a fluid flow? What is the driving force for fluid flow?
Pressure gradient.
It's a pressure gradient. So that means we have a pressure in and a pressure out in order to get things flowing into the system. So what's happening is that we have some volume element flowing in and out of the system. So in order to get this volume element in, so rather this is the density, this will have a mass in. The only way to get this mass with this density into that process is to physically push it in. It is not going to spontaneously just flow into the system. So the energy that it takes to push this fluid in is going to be the pressure, the volume, and the mass. So in this case we have pascals, meters cubed per kilogram times by kilograms. That gives us joules. So the physical act of the fluid flowing into the process actually contains a little bit of energy. Now, if you were stranded on a desert island, and you didn't know, you couldn't remember, you didn't have your thermo textbook, but you knew everything else about thermo except what's the difference between internal energy and enthalpy, and you only had access to internal energy or you only had access to enthalpy tables, it's not going to make a big difference. The PV contribution is not terribly significant until you get to really, really high pressure scenarios. And so in the case of liquids, the internal energy of liquids is almost never tabulated because PV of a liquid is very small because the density is really, really high, which means its specific volume is really, really low. So the PV contribution for a liquid, not a big deal. So when you put this all together, if you were to rewrite this stream right here, and of course the same thing is on the out. So P out, V out, and the change in mass flowing out of the system. So when you rewrite that and you include this extra source of work going into the system, you have a summation of the mass flow rates times by the internal energy flowing into the system times by the PV work flowing into the system plus the kinetic energy, plus the gravitational energy. We then just combine these two terms into enthalpy. That's the driving force for why we actually use enthalpy. So the forms that we will be starting off with most generally the chemical engineering version of the first laws of thermodynamics, this is for an open system. This is the total energy that the system has, that box that I drew, we could draw a line around. How much mass is flowing in with a specific value of enthalpy, how much heat is entering the system, how much work is leaving the system, and then just basically solve the problem. More often than not, we are going to say that this term here we're mostly going to say that that term is equal to 0. For a steady state process, the total energy is not going to be changing, which is good, right? Because if we had a non-steady state process like a boiler for a power plant, that means that the temperature would be continuously going up and down. It means the pressure would be continuously going up and down. And the whole point of having a continuous process is you design it so that it runs at the optimum peak conditions all the time, no matter what. So our goal is almost always to make sure that we have steady state operation. Now this is for an open system. So oftentimes you'll hear, okay, open system means I should use enthalpy. Closed. Yeah, so basically for some reason it like runs out of memory and it just stops the video. So some videos are high quality, some are low quality. All right. How's everyone feel about the first law? Hopefully this should be a recap for everyone. Now we'll move on to the second law of thermodynamics. So the second law has a bit of a problem. You know, it's been described as the most perfect law in all of physics because it's very simple It's never been disproven, and it applies to everything. So here's the problem. How do you define the second law in the most basic fundamental principles, because it does govern everything? Right? You can't define the second law in the form of temperature, because temperature is defined based on the second law. So the challenge of the second law of thermodynamics is, absent a just strictly mathematical derivation, you have to basically define properties that entropy predicts in order to define the second law. So we're going to go through a few of those. Of machines that are not very good. So Clausius in 1854 came up with this definition of the second law of thermodynamics, basically saying that there is no process that can occur where heat can be transferred from a cold body to a hot one. Problem is, temperature is defined based on entropy. So the basics of this here mean that you're kind of putting the cart in front of the horse. A similar definition of the second law from Kelvin and Planck. I guess I don't quite know why they get credit for this one together, because they were at very different times. Have another process that basically says this is not possible as well. Oh, so let me see. So TC has to be less than TH. So this is so you cannot do this process here. An alternative definition of the second law is saying that you cannot have any process where heat is directly converted to work. This is also a no-no, violates the second law of thermodynamics. Again, it relies on definitions that have, this is a little bit better than this one actually. Clausius is pretty bad. But you still have to rely on things like hot and cold. So people are still, more or less to this day, trying to put together a good definition of the second law. So the modern form of the second law a mathematician by the name Theodori. In the past I've written this out, but I'll just read it out because it's a very mathematical heavy and not particularly useful for engineer definition. So this work was titled it was the first what they call self-evident mathematical foundation of thermodynamics. So this is his definition of thermodynamics. In any neighborhood of any state, there are states that cannot be reached by an adiabatic process. That is the definition of the second law from a very fundamental mathematical perspective. So basically what they're saying is that some systems cannot just spontaneously change to other systems. Particularly saying if one system has a higher entropy than the other, you cannot spontaneously go to a state of lower entropy. So it seems unsatisfying because we're basically just stating the second law again in a different way, but more or less the mathematical foundation or postulates of the second law are basically just saying this entropy thing exists, can't go from low to high. Here are the properties that mathematically entropy has to have in order for these definitions to be appropriate. So that gets us to some folks, one guy's from Princeton, I can't remember where else they're from. One's a physicist, one's a mathematician. But even up to 1999, people were still trying to clarify and refine Theodori's approach. Basically from a very rigorous fundamental mathematical perspective, the type of math that I don't understand and it really makes my eyeballs cross, but basically where they go for the approach where they take they say axioms. This is axiom 1, this is axiom 2. If entropy behaves this way, this is what the consequences are. Entropy has to be convex or something, or concave, right? So they go through a big, rigorous definition. I don't want to go through all the details, but I just wanted to highlight the year, which, I mean, 1999 seems like a long time ago, but in terms of thermodynamics, it's really the blink of an eye to modern times, because we started off talking about the 1600s. So the short story is we are still basically struggling to understand entropy. The way that I justify entropy is that I think of entropy in the second law and thermodynamics in general sort of like on the stepping stone to quantum mechanics. So who here has had a quantum mechanics course? Okay, so decent number of people. But who here is sort of the wave function, like the electron wave function? It basically doesn't mean much of anything, right, unless you put a Hamiltonian to it. So the second law in my mind is sort of almost to the abstraction level of a wave function in quantum mechanics, where in quantum you just have to trust that the math is working out for you. Sort of a similar thing with the second law of thermodynamics. We just kind of have to trust that the law is valid, and then we just go with the consequences of what the law basically says. So what I'd like to do is I would like to go through and I would basically like to derive where does this equation come from. Right, this is the starting point for a closed system entropy balance that we will typically see in a chemical engineering or undergraduate thermodynamics textbook, or all thermodynamic textbooks. But where does this come from? I've never seen it described, so I kind of muddled my way through a derivation that I think is useful to highlight where we get it from. So we're going to build a system here where we have a small subsystem here, where we're going to call it has a particular temperature, it has a particular volume, it has an internal energy. We're going to say the volume is constant, so there's no PV work going on in the system, that only energy transfer in the form of heat is going to happen, and that the outside is going to be infinite, it's going to have temperature T, and it's going to be constant. And we are going to derive this form of the second law of thermodynamics. Okay, so we'll start off simple. We're going to look at the first law of thermodynamics. So for this entire universe of my system, I have du. What is du equal to? What is the rate of change of energy of the entire universe? Zero. So what that means is that the rate of change of the system here, plus the rate of change of the surroundings has to equal 0. Of course, one can be positive, one can be negative. So if we rearrange that, any energy gained by the system is lost by the surroundings, or you can move the negative sign over and have it be the same. Right, so the first law basically says energy is just exchanging back and forth. Okay, so now let's do an energy balance on the system. We're going to use our closed system energy balance. How can I simplify this? Well, I'll say du of 1. What terms can I cross out in this balance? Work. Why can't I cross work off? Volume is constant. There is no PV work going on in the system. So that means that du of 1 is equal to the rate of heat transfer. So next, we are actually going to rely on defining what temperature is. So 1 over T is defined as how the entropy of the system changes with respect to changes in internal energy when the volume is being held constant in the system. So if we were to break apart this integral here, we can write that ds1 is equal to du of 1, which is equal to and conversely, we can apply this to the surroundings. Okay. We use our second law of thermodynamics. We say that ds is greater than or equal to 0. So one thing that I have to note here is that entropy has a property where it is extensive, so the more matter you have, the more entropy you have in the system. So in which case here, ds is equal to ds1, change in entropy of the system, plus the change in entropy of the surroundings.
I have a quick question.
Yes.
So in your definition, 1 over t is defined as partial u, constant b.
Yes.
How do you go from the partial definition to then having total derivatives?
Good question. In this case here, I believe the short answer is because they are state functions. So when we break them apart, we can integrate both sides independently, and as long as we're going from the same state 1 to the same state 2, it's okay.
Well, because when we define those, when we make those like temperature definitions, it's basically like the total derivative of the internal energy function, right?
For, you mean like the total differential for like a du, for example?
Yeah, the du is like partial u, partial s, ds plus. But would all those other terms then be 0? And is that why? I don't know.
So in the case, oftentimes when we're writing out these sort of thermodynamic partial derivatives, the base assumption in thermodynamics is that everything is a function of everything else. And that's why you kind of keep those partial derivatives saying, if we do this term here, where only these two variables are changing, you're holding this third one constant. That's kind of keeping in line with the Gibbs phase rule. When we're breaking it up like this, in this particular case here, we only have basically one function depending on the other.
Right.
So that in that case,
constant.
Yeah, in that case we can do the total differentials.
So I was just confused because like I've seen the n also, so you can't do that.
In which case the
like if you have the number of moles as another variable.
If that's the case, then yeah, then you would have another variable changing in the system.
Yeah. Okay.
The one thing that's nice about thermodynamic math is that it's a little bit hand wavy to some extent.
Yeah. So
it's good in the sense that if you kind of are confident in what you're doing, you kind of switch those things around, but when you actually get into the mathematics of why it's not particularly as apparent. But I think in this particular scenario here, it's because we're only differentiating two state functions.
Yeah, I'm convinced.
Okay.
Thanks.
Good question. Those are the questions that always worry me, where I have to go back and think what's the difference between the two. All right, so let's finish up our derivation here. The total change of entropy in the system is how much entropy is changing in the system plus the surroundings, I guess the total entropy of the universe, rather, to say. And then we know this has to be greater than or equal to 0. So what we're looking for here is we want to know what is the entropy of the system itself. So we just take this here, move it to the other side. So we're going to say this is actually greater than or equal to Q dot over T. Or we could also write this as ds is equal to Q dot over T plus S gen, saying that greater than or equal to 0. And then if we want, we can just add on a little dt to the bottom of it. The notation here in thermodynamics, why we don't ever put, typically we don't ever put that denominator, is because we know that this holds true for everything. Temperature, pressure, volume changes, internal energy changes. Right, so this is just a quick-hand notation. We drop this because we know that in thermodynamics it applies to any changes of other thermodynamic properties or time.
What's the subscript under this?
This one here?
Yeah.
This is supposed to be generated. G-E-N.
Okay.
Rate of entropy generation. So you can either say that this term always has to be positive, or if this is negative, the generation has to be greater. Right? So it's two interchangeable ways that we can write this out. Oftentimes I find that working with inequalities is confusing, so I probably prefer just including the S-gen, knowing that it has to be positive. If you ever have a negative entropy generation, then there's an issue. So the only thing that changes here between this and an open system S-balance, entropy balance, is that in the open system, we have to include the possibility of entropy flowing in the form of molecules. Let's see, and then we'll keep the same notation. K, K, K. In this case here, I've switched up the nomenclature just to be confusing, right? Where entropy with the underbar is equal to joules per mole Kelvin. So underbar per mole, hat per mass. Just following that. Don't get mad at me. I'm just following the standard notation.
I have one quick question.
Yes.
So the top of your rightmost column, the second line that you put a box around.
Yes.
How did you get there?
How do we get to this equation right here?
Yeah. Sorry, I'm just not seeing.
So what I did here is basically said that this term has to be greater than or equal. So another way to, I could also write it here, I think, let's see. ds of 1 minus q dot over t is greater than or equal to 0. So they move this over to the other side of the equation. And so then whether it has to be greater than or equal to this term right here, instead of keeping the inequality present in the equation, I'll just say, you know what, I'm just going to add in this other term that has to be greater than or equal to 0 to make the inequality go away.
Oh, so you're adding something to make it true.
Yes, yes. So I'm creating this variable here called entropy generated that has to be greater than 0.
Okay.
So if this term is greater than 0, then that would mean that this side is always going to be greater, sorry, this side always has to be greater than 0.
Right, yeah, because okay. Or 0.
Or 0, yes.
Zero.
So for a reversible process,
Okay.
entropy generation is 0. That is the definition of a reversible process, is that S-gen is 0. There's no entropy generated.
And then I guess the last thing is you have q dot in the lower one and q dot in the other one, but you took the time rate of change.
Yes, so
Should one of those not be q dot?
no, I think they should all be q dot because you're still looking at the rate of, so we're still looking at a differential form. We're looking at the rate of heat into the system. So if you wanted to change this as a function of like pressure, so the convenient thing about thermodynamics, and this is what I think throws a lot of people off and it brings up kind of transitions to a good point, we get confused because we think if I want to increase the pressure of the system, in our minds, we're thinking about how would I physically do that and how long would it take and at what rate would I pressurize it. But it actually doesn't matter for thermodynamics. So we can think of it as a function of time or we can think of it as a function of pressure, knowing that because it's a state variable, it doesn't matter how we get to those two endpoints. So with that being said, all these questions kind of hover around this term right here. You will almost never use this term. Right? This term is something that in almost all the problems that I assign in class, you will never be using that term to basically solve the problem. Maybe a handful. I've got one example that I like to do with the heat exchanger where you actually use that term. But in general, this only complicates things for students. Almost always does it complicate things. Because it is weird, because the whole point of thermodynamics is that we don't actually have to care how we go through a process. We just have to know what the endpoints are. And that's why thermodynamic math is super fun. Because if I want to get delta S, I just go, oh, I'll just integrate ds. From where? How do I do it? Oh, I'll do it from state 1 to state 2. But what's state 1 and state 2? Well, I don't know. This position to that position, right? You can just basically do that. So when you look at this here, this is delta S, S of 2 minus S of 1. I get to define all the thermodynamic states here, basically. So this could be temperature 1, sorry, pressure, temperature 2, pressure 2. This could be temperature 1, pressure 1. But you can be really free form with your mathematics and thermodynamics because they're state functions. It doesn't matter how you go from point A to point B. So when you integrate ds, you literally just slap on an integral, say where you want to start from, where you want to end from. That delta S is S of state 2 minus S of state 1. So for most all classical thermodynamic problems that don't involve multi-component, multi-phase systems, all you have to do is take a steam table or some sort of a table, if you have access to it, that has all your enthalpy values, all of your entropy values, and just take this equation here, just look numbers up. That's all you have to do. So that's why I don't like to spend a lot of time talking about power cycles. In fact, we don't actually go through any examples of power cycles in class, but I'll give you homework problems on it. But I'll make sure that I give you homework problems for fluids that you have access to thermodynamic data tables. Refrigerants, steam, those types of things. Is that making sense? Right, so solving these types of cycle problems really is just a matter of writing out the mass balance, the entropy balance, and looking numbers up out of the table. That's not the cool part of thermodynamics in my mind. The cool part about thermodynamics is how do we predict what the entropy is? How do we predict what the internal energy is? How do we use this information then to predict phase transitions and separation processes? That's much more complicated. And so a lot of the time we're going to spend on the class is how do we actually use an equation of state like the ideal gas law, like the van der Waals equation, to predict entropy and to predict internal energy. If you have the tables, the battle's already done. It's a trivial process to do the rest of it. All right, in the last little bit of class, what we're going to do is we're just going to quickly use our modern form of the second law of thermodynamics to disprove some of these processes. So let's look at Clausius's. So in terms of his, this is what we're talking about here. We're saying that we cannot have a process that transfers energy from a cold reservoir to a hot reservoir. Okay? Yes, that's right. So let's look at an energy balance. So I guess, let's see here. Well, let me redraw it because I think I have a slightly different nomenclature that makes the answer look pretty. We have a hot reservoir. We have some sort of a magical process. There's a cycle, a steady state cycle, some machine that some inventor comes up with that is magically going to do this task. I'm defining the heat flowing into the process. From the hot side is QH, defining the heat flowing into the process from the cold reservoir as QC. So our energy balance, the rate of change of energy of the system is going to be 0. It makes our life easier, imagining that this is some sort of a magical steady state process. All that's saying is that any heat that transfers in from one side has to leave on the other side. Energy balance says this process is totally okay. And this is why, more often than not, describe the second law as really the driving force of thermodynamics, and the energy balance is really just kind of a thing you can't violate, just like the mass balance. However, let's look at our entropy balance. The change in entropy of this system, and this is one of those instances where we are actually going to use this Q over T term. Right, the entropy balance says that this contribution here, the rate of change of entropy for the entire system has to be greater than or equal to 0. This is strictly just a mathematical application of this closed form of the entropy balance, which of course relies on the fact that temperature is defined based on entropy properties. So if we do our math here, this is equal to QC over TC minus QC TH greater than or equal to 0. We can get rid of that. We'll have 1 over TC minus 1 over TH greater than or equal to 0. And then finally, 1 over TC has to be greater than or equal to 1 over TH. Do our cross multiplying, and the hot reservoir has to be hot. The cold reservoir has to be cold. So one way to think about entropy is that, so we talk about entropy in the sense that it is kind of the randomness of molecules. And in terms of how the second law is defined about how the rate of entropy changes, what we're doing when we're transferring energy from one reservoir to another reservoir, hot molecules already have a lot of sort of randomness associated with it. Cold molecules don't. So if I have a kilojoules worth of energy to give to either a hot reservoir or a cold reservoir, which of those two causes more entropy increase? Okay, all those in favor of cold. All those in favor of hot. All those not voting. Come on, guys, commit to one or the other.
What was the question?
So, if I have a kilojoule worth of energy and I want to give it to a cold reservoir or a hot reservoir, which of those two will the entropy increase the most? Okay, I want everyone
Heat
to
rate's
vote.
the same. The
Heat,
rate of
heat,
heat
yeah,
transfer is the same.
The rate of heat transfer is
So it's
exactly the
inversely
same.
proportional to temperature.
Yep.
So
So
a higher
you-
temperature would be a lower entropy.
So let's vote. Who says that the cold reservoir gains more entropy? Stick them up proud, guys. Okay, who says the hot reservoir gains more entropy? So everyone's chickened out of the hot. There's a super easy way to answer this question. So if I have entropy as a function of temperature, what does it have to look like?
This one.
It looks
It's
like
always convex, which means that if I have the same material with a similar thermal conductivity, right, my entropy, rate of entropy increase is always going to be higher at lower temperatures. So that's why, in this instance here, right, energy, when you transfer energy from a hot reservoir to a cold reservoir, the cold reservoir has to gain more entropy. Right, so that's why you could never take away a ton of entropy here from a cold reservoir and then give it to the hot reservoir, because it'll never make up for that difference in information. Right, so one way to think about entropy is kind of like the temperature by which you transfer energy has kind of like a memory associated with it a little bit, because it's telling you how much am I changing the entropy of the source and the destination. Does that make sense? But I think, in my mind, one of the most confusing things about entropy is that it's a state function and it's also not conserved at the same time. So how can we actually have something that's not conserved be generated? How can something be a state function where you can, acutely predict its properties, but then you can't actually conserve it? So I think that's one of the confusing things about entropy, but I don't know, you just gotta get over it. Or just don't think about it, maybe that's the better way, just don't think about it.
You just get over it.
Just get over it. All right, let's disprove Kelvin and Planck's. Let's see, All right, so they're saying basically that we have some magical process where we are transferring heat to it, and that magical process is converting it directly into work. So I'll skip ahead a little bit on some of the steps. So our energy balance, the rate of change of energy in the system, as we're going to say, is equal to 0. Based on how I have drawn my arrows, Q is going into the system, work is leaving the system. I more or less am just doing this so it comes up with pretty looking answers, but noting that the negative sign doesn't really matter. So according to the energy balance is dumb. It basically says, yep, no big deal, this looks like it's going to be a great process. Where do I sign up? Looking at the entropy balance, there's a couple of ways we can do this. I prefer looking at it this way. The rate of change of entropy in the system, we have heat being transferred to it at a particular temperature, so that heat kind of has a memory a little bit. So the way that this is drawn here, the rate of entropy generation in this case is negative. The only way that the rate of entropy generation is positive in this scenario is if, in fact, our signs are reversed. We can convert all mechanical work directly into heat. That's totally fine. But we cannot convert it the other way because temperature can never be negative. Again, this is also sort of, they call it the third law of thermodynamics as well, but it's also a consequence of the second law of thermodynamics. You can never have negative temperatures. So if temperature is always positive, that means the way that I've drawn my arrow in Q, in this case here, S gen is less than 0, so this is a big no-no in terms of thermodynamics. So the second law is the fun, creative one. The first law is just sort of a boring rule to follow. All right. So we've got one more task that I wanted to go over, but we'll do this first thing on Friday, deriving the Carnot cycle efficiency. Basically, we're going to be doing exactly the same thing, but in this case, we're going to draw a process that is actually real. So the Carnot cycle, the derivation is based on very similar machines, but in this case, we have a cold reservoir, we have a hot reservoir, we have heat going into the system, we have heat leaving the system, and we are pulling work out. So using the energy and entropy balances, we can derive the efficiency for the Carnot cycle, and we'll do that when we first start on Friday. All right, so that kind of covers our gentle introduction to thermodynamics. We will be picking up the pace pretty rapidly. Like I said, I will not be going over a ton of examples, especially examples that most of you have seen many, many times over again. The challenge of thermodynamics, I'll reiterate, is not in applying the first and second law. The challenge in thermodynamics is predicting fluid properties. So modern thermodynamics nowadays is basically using molecular level simulations to predict properties for compounds that we don't want to synthesize. It may take a chemist an entire PhD to synthesize a particular compound. Now, wouldn't it be terrible if that compound didn't behave the way that you wanted it to behave? Right? You invested years of your life, countless hours and weekends in the laboratory, and it just didn't do what you wanted it to do. It didn't have the right heat capacity, it didn't have the right thermal conductivity, it didn't have the right isothermal compressibility, right? It was just off. Classical thermodynamics can worry themselves about macroscopic properties. So we can use those macroscopic properties to define better for refrigerants, better materials to solubilize certain compounds, right? So the real power of thermo is predicting how entropy and enthalpy change as a function of temperature, pressure, and density. When we go later on in the class and talk about statistical mechanics, the objective there is, now let's pretend that the world is made up of these things called atoms and molecules. we can design atoms and molecules to behave in the way that we would like them to behave, do all sorts of cool self-assembly processes, absorb energy, have interesting rheological properties. So modern thermodynamics now is more so focused on performing computer simulations to better predict properties that way. So you don't have to synthesize the molecules to know if this is going to work. So that's really the fun part. Looking up steam tables, I don't find that to be particularly challenging, so I don't emphasize it too much, but we'll go over a few examples in the homeworks to sort of grease the wheels to remind you guys what you're leaving behind in undergrad thermo. All right, that's kind of a really brief overview of how all this fits into what we're going to be accomplishing throughout the rest of the class. All right, have fun in fluid mechanics. Oh, you have a question?
In that equation, why ds to be taken as 0?
ds is, which one here?
Yeah, the third equation.
1, 2, 3 here. So ds, it was not greater than or equal to 0 because I'm including the entropy generation rate.
No, but why you equated both the second, all this, how did you get to the next step?
How did I, yes. So this is going to be equal to 0 because it's going to be steady state. Yeah, so when this is, sorry, yeah, I was a little bit precise. Yeah, when we take this as a function of time, the total entropy of this system is not going to change. Because if anything in the system changes as a function of time, that means it's going to either be growing in size, shrinking in size, and all those different things. So we want to take it as a steady state process. Yes, so thanks, good question. All right, see you guys. I'm getting that done.